next we start with the algebraic properties of real numbers. So first of all, we will define field. Now what do you mean by a field? You are having any non-empty set S. So we consider two sets, one is S, one is all the non-zero elements of S, means we delete the zero number from the set S. Now these two sets should be commutative group with respect to the two operations. One is the addition and other is the multiplication. Right? It should satisfy the properties that it should be commutative group with respect to the operation plus and multiplication is distributive over the addition. So first of all, these two operations should be defined on a set S. Now what is the meaning of defined? So here we take S to be real numbers because we are talking about the algebraic properties of real numbers. So we will check whether R is a field or not. So now just see, let's suppose your S is the set of real numbers R. We have to define the binary operation addition and multiplication on the set of real numbers. Now this set should be closed under these two operations. Means what? If you take any two real numbers, you apply the binary operation addition, you get a new number and it should belongs to the set of real numbers. Means it should be a real number after taking the addition. Similarly, if you are having two real numbers, you apply this multiplication operation on the elements of these two. After multiplication, you will have a new number which is also belonging to the set of real number, means which is also a real number. So if these two conditions holds, it means the operations addition and multiplication, they are defined on a set of real numbers, or a set of real number is closed under the binary operation addition as well as multiplication. So first of all, these two operations should be defined on a set, and with respect to these two operations, this R should satisfy some properties. So now see the first property, it should be commutative group with respect to both the operations, with respect to addition as well as multiplication. That means what? If you consider two elements from the set R, you apply the operation addition, x plus y is same as that y plus x. Both are same. Either you add x in y or y in x, one and the same thing. Similarly, it should be commutative with respect to, you can say here the commutative property only. It should be commutative, should satisfy the commutative property with respect to addition and multiplication. So if you consider any two elements from the set R, you apply the operation addition, it should satisfy this commutative property. Means either you add y in x or x in y, one and the same thing. Similarly, with respect to multiplication also, so means either you multiply x with y or y with x, both are same. Position doesn't matter, right? So both these hold in case of real numbers. Number two is the associative property. So associative property should hold with respect to the operation addition as well as multiplication. Means what? If you consider any three real numbers, you apply this, first you add y in z and then with x is same as that, first you add x in y and then with. Similarly, with respect to multiplication, x dot y dot z, means you take the multiplication of y with z and then take with x is same as that, first you take the multiplication of x and y and then with z. So if this thing hold with respect to the operation addition and multiplication, that means this set of real numbers, it satisfies the associative property. And we know that in case of real number, this thing hold. Is it clear?
Yes, ma'am.
Now the third. Okay. Now the third property is the distributive property. Means what? if you take any three elements from the set of real numbers, you first add y and z and then you take the multiplication with x is same as that. First you multiply x with y, x with z, and then you add these two numbers. So one and the same thing. So this is called distributive property. Right? The next is identity should exist. So that means there are two distinct elements in set of real numbers denoted by कौन से हैं? They are 0 and 1, such that for each x in R, what we have, whenever you add 0 in x, you will have again x. And similarly, when you multiply any real number with 1, again you will have the same number x. So 0 and 1, these are two identities with respect to the operation addition and with respect to the multiplication. And clearly 0 and 1, they are the real numbers, so they exist in a set of real numbers. So that means identity exists in case of real numbers. Now the next is, for every x belonging to R, there must exist some y in R, and this thing hold, such that your x plus y is the identity with respect to the operation addition. And with respect to the operation addition, we know that 0 is the identity in case of real numbers, right? So here your y is the inverse of any real number x with respect to the operation addition. Right? So here this y is the this y is the inverse of x with respect to the operation addition, and 0 is the identity with respect to the operation addition. So for every real number, there must exist some y in R such that this thing hold. So then this y is said to be the inverse of x. Is it clear?
Yes, ma'am.
Now the last property, can I move to the next slide?
Yes, ma'am.
Okay. Now the last property is, for every non-zero x in set of real numbers, there exists y in real numbers such that the product of these two should be 1, because 1 is the multiplicative identity, right? So 1 is the identity with respect to the operation multiplication. So here this y is said to be the multiplicative inverse of this non-zero number x, and we know that this exists in case of real number, because since x is non-zero, so 1 by x is also a real number, so y is nothing but 1 by x. So this holds in case of real number such that the product of these two numbers is 1. Similarly, here we know that whenever your x is any real number, then minus of x is also a real number. So this minus of x, negative of this x, is a real number, and this will become the additive inverse of the real number x, such that their addition is the identity which is 0 in case of real number. Okay, so since set of real numbers, they satisfy all the properties, that it is commutative, associative, identity, distributive, right, and inverse exist with respect to addition as well as multiplication. So therefore your set of real number together with the two operations addition and multiplication is a field, right? For multiplication you require that the set of non-zero real numbers. Is it clear to all of you?
Yes, ma'am.
Now some consequences. And you know that in case of real numbers, this thing holds. That if you have a plus b is same as that a plus c, then this implies what?
B is equal to
B is equal to C. So these are some algebraic properties. We know that this thing hold in case of real number. Whenever A plus B is same as that A plus C, B is always equal to C. So with respect to addition, we know that this thing hold. Similarly, given any two real numbers, AB belonging to R, there exists exactly one real number X such that your X plus A is B, right? If you are having any two real numbers, exactly एक X exist करना चाहिए such that whenever you add that X in A, you will have B. For example, let's suppose we have taken real number A to be as half and B to be 3, let's suppose. So what will be the value of X? Which number you will add in A, and that should be only one number such that you will have B. So that will be 3 minus half. This is the value of X, and clearly this is a real number, right? So from here we can find out the value of X. This will become B minus A. So for any two real numbers A and B, we can always find a real number X such that we can write X plus A as B. Is it clear?
yes, ma'am.
Now the third is we know that B minus A, it is same as that. You can write as B plus negative of A, one and the same thing. Similarly, minus of A is same as that A. And all these are the real number. In case of real number, this thing hold. A times B minus A is same as that A into B minus A into C. 0 times A is 0, is same as that A into 0. A into B, if your A into B is equal to A into C, and it is given that A is a non-zero number, then this implies what? You can divide by A to both sides, you can cancel out A, and you will have this is same as that B is equal to C. So condition is this, that A should be non-zero, only then you can cancel out the terms to the left side with the right side, right? So whenever your AB is equal to AC and A is non-zero number, you can cancel out both sides and you will have B is equal to C. So these are the operations you can say on the real numbers, and these things hold. So these are some algebraic properties of R. The next is same as we have done in case of addition. Similarly, we will have in case of product also. Whenever you are having two real numbers with one number is non-zero, then there always exists exactly one X as a real number such that A times X is B. Means if your A is non-zero, we can always find a number X. Whenever you multiply with A, you will have the next number which is B. So that means you can choose X to be as B minus A, provided A is non-zero. Now the ninth is, if your A is non-zero, then the inverse B by A, it can be written as B into A inverse. Or same way, A inverse is nothing but A, provided A should be non-zero. Only then you can talk about the A inverse, 1 by A. right? The next property is, if AB is 0, then either A is 0 or B is 0. If the product of two real numbers is 0, then this implies that either A is 0 or B is 0. That might be both are 0, but this thing always holds that either A is 0 or B is 0. So these are the operations which hold in case of real numbers, and these all properties hold with respect to the real numbers. Now the next is the order properties of R. Means we can compare two real numbers. So that is the order properties of R. So you are having, you know that this set of real numbers, they are field, they satisfy all the properties of field. So this R, which is a field, now it is said to be an ordered field if it's satisfying some properties. So you can write down a field R or S, whatever. We can denote this by set S, and especially we can call this as R in case of real numbers. This is an ordered field if it satisfies the following properties. Now, what are these properties? Now, the first is the law of trichotomy, that says that whenever you are having two elements from the field, let's suppose A, B, they are any two elements. So for any two elements A, B from the set S, there must hold one condition, that either A is greater than B, A is equal to B, और A is less than B. अगर आपके पास कोई भी दो नंबर हैं फील्ड से, तो इन तीनों में से एक केस ऑलवेज होल्ड होगा, एक प्रॉपर्टी ऑलवेज होल्ड होगी, या तो A बड़ा है B से, या A इक्वल टू B है, या फिर A है लेस देन B, right? This thing always hold. So these are the ordered properties. We can compare the two real numbers or the members of any field S, right? So any field S is said to be ordered field if it's satisfying some properties. First one is the law of trichotomy, that says that if you have any two elements from the set S, then one and one, only one of the following is true. Which one is that? Either your A is strictly greater than B, or they are equal or less than B. This property is clear? Now the next property is the transitivity property. Now what do you mean by transitivity? If you are having three numbers from the field, so this will be true for every three elements from the set S. They may be equal, they may be different. So if we have these three conditions, we have these conditions that A is greater than B and B is greater than C. So this is the transitivity property that says that whenever you are having three elements from the field, if A is greater than B and B is greater than C, then this implies that A is greater than C. अगर A B से बड़ा है और B C से बड़ा है, तो clearly A जो है वो C से बड़ा होगा. Third property is the compatibility of order relation with addition composition. compatibility of order relation with addition. This says that whenever you are having 3 elements from the set S, and this is true for every 3 elements from the set S, whenever your A is greater than B, this implies A plus C. You can add a number, it remains greater than B plus C. So the order remains the same if you add an element to both sides. Similarly, in case of multiplication, so the compatibility of the order relation with respect to the multiplication. Now this says what? For every A, B, C belonging to the set S, A greater than B and C is positive number, C is greater than 0, then this implies that A times C is greater than B times C. So if your C is any positive number, you can multiply both sides and the order remains the same. If A is greater than B, then AC is also greater than BC. So these are some order properties of R or any field, you can say. If any field satisfying these 4 properties, then that field is said to be ordered field. Clear? Is it clear?
Yes,
Yes,
ma'am.
ma'am.
Can you give any example other than set of real numbers as an ordered field?
Any subset of R can be an ordered field.
No. Set of natural numbers, they are the subset of real numbers. Are they field?
No. Rational numbers.
Yes, set of rational numbers, they are ordered field.